Natural intelligence. One goal of artificial intelligence is to build machines that can operate in the real world, with all its noise and uncertainty. Much of what we want machines to do, see, recognize, navigate, move, coordinate is already done very well by simple creates. In this unit, we look at how such creatures achieve these goals and start to understand how we can build machines with the same capabilities. M366-2, Natural Intelligence. Introduction. In this unit I will cast my net into the natural world by examining a number of short case studies, all based on observations of the behavior of animals. I want to probe these for ideas that might help us to reconsider our rather narrow conception of intelligence. I also want to challenge some commonly held ideas and distinctions. This is not a unit on biology, but it is a unit on how biology can inspire, change, improve and develop the computational techniques we need for truly intelligent computer systems. Learning outcomes. After studying this unit you will be able to write a short paragraph outlining a broad definition of natural intelligence, rooted in some of the features of natural systems. Give a number of examples of natural systems that seem to be purposeful, systematic and ordered. Give contrasting definitions of the words natural, artificial and living, explaining some of the difficulties that arise in drawing firm boundaries between them. Write a short definition of the term nouvelle AI and contrast this with symbolic L. 1 Preliminary examples. The best way to start is by thinking about the following two case studies. Case study 1, flocking and migrating birds. At one time or another, you will have witnessed the sight of a flock of birds, maybe hundreds strong, wheeling in the sky. Perhaps you didn't give it a second thought, but bird flocking does seem quite a mysterious phenomena. The birds all keep formation, change course together, steer on the same heading. They seem to be moving as a single group, but there is no leader, no observable external guidance and no obvious way in which the birds might be communicating across the flock. Even more striking is the phenomenon of migration. Most bird species migrate northwards in the spring to breed, and south in the winter to warmer climates where food will be plentiful. Figure 1 Canada geese in flight. Some species travel by day, others by night. Some fly in immense flocks, others alone. Many cover enormous distances. The Arctic tern Sterna paradisei migrates from Maine in the USA to the coast of Africa and then down to the Antarctic Circle, traveling as much as 35,000 kilometers a year. Most breeding and wintering grounds cover relatively small geographical areas, yet the birds find their way to them unerringly, year after year. For example, the greater snow goose Chancea relescens atlantica breeds in a very specific region of the Canadian high Arctic, from the Fox Basin to Alert on northern Ellesmere Island. They winter along the United States Atlantic coast, migrating more than 4,000 kilometers, in flocks of between 35 and 1,000 birds, depending on the season. Figure 2 Snow goose migration routes. How birds are able to navigate with such accuracy is not fully understood, but most species are thought to use a number of range and direction finding strategies, including steering by visual landmarks such as coastlines, rivers or mountains, setting flying courses by the sun especially at sunset and stars especially the pole star and the constellations around it, following the Earth's magnetic field. Iron-based minerals in birds' skulls enable them to fly north along magnetic field lines. Some birds, such as petrels, also use their sense of smell to navigate, but only as a supplement to the mechanisms described above. Case Study 2, Raiding Army Ants. The many species of carnivorous army ants live in colonies, maybe up to 1 million ants strong. Army ant nests are often referred to as bivouacs, because they are not earth constructions like those of other ant species. They are formed by the ants themselves, clustering together to form walls, fastening onto each other using their mandibles and claws on their legs. Despite being more or less blind, army ants search for prey in immense, highly organized groups, either swarms or columns, depending on the species. In a column raid, the ants spread out from the colony along a single trail from which foraging worker ants branch off along smaller columns. A swarm raid also starts along a trunk trail, which divides into numerous columns that then recombine into a single advancing swarm front. Figure 3 army ants on the march for regularity, organization and sheer savagery. Nothing quite matches the swarm raider Eber Kelly. A single colony may consume 100,000 prey items a day and bring back as many as 30,000 from a single raid. At dawn, pioneer ants set out, first along a base column connected to the bivouac and then fanning out in a complex network of columns along the swarm front up to 15 meters long and 2 meters deep. Individual ants move forward from the front and then retreat. And as each ant turns, another passes it, extending the front further. Figure 4 army ant column raid. Bee swarm raid smaller insects and even relatively huge creatures such as cockroaches, scorpions, grasshoppers and earthworms are flushed out, overwhelmed and stung to death by the advancing mass. Their corpses are sawn up and the pieces transported back to the colony by streams of workers along a labyrinth of trails behind the main front. Unbelievably, army ants have been observed to kill and dismember chickens, goats and even pigs, if the animals have previously been injured and are already helpless. Sack 1. From your own general knowledge, try to think of one or two other examples of similar behavior to that described in the above case studies. Answer. One doesn't have to be a zoologist to know that examples abound. Birds and termites build complicated nests. Whales and bees carry out remarkable feats of navigation and communication. Fish and mammals such as wildebeest travel and defend each other in apparently organized schools or herds. Exercise 1. What seems significant about behaviors like these, as compared to some other natural process, such as an avalanche, the flow of a river, the piling up of rocks by a glacier, etc.? Note down some general characteristics that both the above case studies seem to have in common. Comment. Obviously there are key differences between the behavior of an ant swarm, say, and an avalanche or any other purely physical phenomena. First, the swarm seems to be purposeful. All that activity is unmistakably directed towards a clear and defeating of the colony. The same is true of the movement of birds. This certainly can't be said of avalanches, rivers, and so on. Their actions seem to be governed by chance and the results are haphazard. Second, the behavior of the animals in the case studies looks systematic. At first glance, an ant raid might look like a boiling confusion, but, as we have seen, it follows a very regular pattern. So too do the flight patterns of the birds. Such activity can lead to complex and structured results, such as the elaborate nests of termites or birds. There can be no argument that the natural world is full of such purpose and order, but purpose and order are surely two characteristics we might associate with intelligent behavior. To natural intelligence. Before we go on, we should perhaps remind ourselves of what intelligence is. Exercise 2. Write down a brief summary of the key characteristics of intelligence as the concept is understood in conventional L work. Comment. Symbolic L is based on a certain conception of human intelligence, on a general understanding of the workings of our own minds. As sentient beings, we know that we bring special abilities to the world. We use language and logic to plan, communicate and carry out complex tasks. We reason about the present and the future. And we respond flexibly to new situations or unexpected developments. To sum this up, these are some of the presumed basic characteristics of human intelligence in the broadest sense, characteristics that conventional L seeks to replicate on machines. Knowledge. Rational thought using symbols to reason with, as in logic and mathematics. Language using symbols to communicate in speech and writing. The ability to make plans, design and foresee. The ability to learn specialist knowledge and skills. But although we might not be inclined to call ants or geese intelligent in any of the above senses, something more than simple randomness is clearly taking place in the behavior described in the case studies. So perhaps it may be necessary to try for a rather more inclusive understanding of the idea of intelligence. Exercise 3. To what extent do you think a chimpanzee could be called intelligent? What about a dog, an insect? Do you think there could be any alternative conceptions of intelligence, or is human intelligence the only sort possible? Comment. Chimpanzees might not seem to be capable of the kind of symbol manipulation that we think of as typical of the human mind. However, the evidence that they possess an intelligence in many ways like our own is compelling. They live in complex social groups in which status, rank, sharing, cooperation, deception and manipulation all play a part. They make and use tools, can solve complex problems and can be taught a grasp of certain limited forms of language. It's hard to deny that they have sophisticated minds. Dogs, as we know, can learn complex tasks, display emotions, perform feats of recognition and problem solving, and learn to respond to language of a simple kind. But we would probably balk at the idea that dogs' minds function logically or that they contain symbolically encoded knowledge. As you've seen, insects such as ants display highly organized mass behavior, and some insects even seem to have basic learning capacities. But no one in their right mind would be inclined to call an individual insect with its tiny, almost non-existent brain intelligent, or to suggest it uses logic or symbols. Clearly, the issue is a complicated one. On the one hand, few if any creatures seem to possess anything resembling the human capacity for rationality, language and knowledge. On the other hand, we see all around the natural world feats of problem solving, construction and organization that are often startling. And the idea that humanity stands completely apart from the rest of creation, is unique and unrivaled in its status and abilities, does not sit well with the 20th century mind. When Shakespeare wrote in 1603, "What a piece of work is a man! How noble in reason! How infinite in faculty! In form, in moving, how express and admirable! In action how like an angel! In apprehension how like a god! The beauty of the world! The paragon of animals!" Source: Shakespeare, Hamlet 11. He was expressing the standard view of the time. This belief was expressed with blunt clarity in the words of the 5th century church father, St. Augustine. If, when we say, "Thou shalt not kill," we do not understand this of the plants, since they have no sensation, nor of the irrational animals that fly, swim, walk, or creep, since they are dissociated from us by their want of reason, and are therefore by the just appointment of the Creator subjected to us to kill or keep alive for our own uses. Source: St. Augustine of Hippo, The City of God, Book I think few of us would be comfortable with this now. Since Darwin, we are much more inclined to see close links between ourselves and the rest of the natural world, to view our abilities and those of other creatures as all part of a continuum. And in directly comparing our minds to those of animals, usually to the animal's detriment, we may be making a deeper mistake. Many ethologists' ethology is the comparative study of the behavior of creatures, including humans, living in their natural environment. Argue that such comparison leads inevitably to anthropomorphism, seeing intelligence only in behavior that resembles our own, dismissing everything else as instinct or some such word. But the truth is that every species is specially adapted to the specific problems that it confronts. The abilities of, say, a pigeon and a lion are simply not comparable. They inhabit quite different mental worlds. Ludwig Wittgenstein once wrote, cryptically, "If a lion could speak, we would not understand him." But you can see what he meant. How could we possibly understand a lion's mind? Its purposes and ours barely intersect at all. Perhaps the best way to investigate this further is to consider in detail some very broad qualities that we might associate with intelligent behavior. In my answer to exercise 1, I suggested that the case studies demonstrated behavior that is purposeful and systematic, and leads to ordered results. In the next 3 subsections, I will look a little more deeply at each of these qualities and consider what they might tell us about intelligent behavior. 2. 1. Purposeful behavior. The behaviors touched on in case studies 1 and 2 seem to be aimed towards some specific goal, reaching a safe environment, the recovery of prey, and so on. We can call the sort of behavior goal-directed. It can be found everywhere in nature. However, we should be careful. The term can be used to cover a whole range of different cases. Consider the following 3 case studies. Case study 3, tool using primates. Most non-human anthropoid primates, monkeys, apes construct and use tools. Chimpanzees, for instance, use sticks to break open termite nests, pick the locks of their cages, and push away dangerous or unpleasant objects that they would rather not touch. They use leaves to clean themselves and food items as bait. If one is available, they will use a stout rod to prise apart the bars of their cage so that they can put their heads out for a better view. A screwdriver dropped into a chimp's cage may be used as a spear, hammer, probe, mill, toothpick, or for any other purpose the chimp can put it to. Orangutans, however, prefer to hide the screwdriver and then barter it for a food reward from their keepers. Gorillas will first try to eat the screwdriver and then ignore it thereafter. However, gorillas in the wild use sticks as weapons and, in captivity, can be taught to store water in containers. Figure 5a chimp cracks nuts with a hammer. Both chimps and orangutans can make strategic use of tools to accomplish goals such as obtaining food, often devoting a lot of time and experiment to the problem. They will use sticks to reach out for food outside their cages, searching for longer sticks or even joining sticks together, if necessary, until they have an instrument long enough to rake the food towards them. If food is suspended above them, they will make a stable stack of objects, or balance a pole, and then climb it to reach the goal. Case Study 4. Shellfish-eating birds. The oyster catcher Haematopus australis is a shorebird that feeds mainly on mussels and other shellfish foraged from the shoreline. An obvious problem for feeding behavior of this kind is opening the shell to get at the edible parts inside. Studies of oyster catchers have revealed that they break open shells by two means. The shells of mussels washed up by the tide onto dry land tend to be tightly closed. In such cases the bird will move the shell to a dry place where the sand is hard enough to provide support, turn it over so its thinner and more fragile underside is upwards, and then hammer it open with its bill. Mussel shells fished out of shallow water are generally slightly open. The oyster catchers prise the shells of these specimens open by inserting their bills into the crack and cutting the abductor muscle which holds the shell closed. Careful observations have suggested that an individual oyster catcher specializes in one or other of the above techniques. This appears to be behavior learned from the bird's parents. Many species of gull open shells by dropping them on a hard surface from a height of several meters. Herring gulls Larus argentatus are particularly good at selecting suitably hard dropping zones, such as rocks, pavements and car parks, and will generally choose the right altitude from which to drop the shellfish, depending on the size of the target. If the shell fails to break, they will pick it up and try again. Crows will drop whelks only onto certain rocks, choosing their target from the point of view of size, flatness and distance from the waterline so that edible fragments don't fall into the water. They prefer to drop from a low altitude, so that the edible parts are not widely scattered, even if this means they have to repeat the drop many times. Case Study 5. Plume Tracking Lobsters. The American lobster Homarus americanus inhabits rocky, shallow water coastal habitats that provide adequate food and shelter from predators. They hunt for food at night, their diet including fish, crabs, clams, mussels, sea urchins and sometimes other lobsters. Their nocturnal behavior, along with the fact that they only have rudimentary eyesight, means that lobsters have to rely on their highly developed sense of smell to detect prey, mates and predators. The strategy they use is known as plume tracking. Lobsters use structures called antennules, as well as odor-sensitive hairs on their bodies, to detect water currents known as plumes bearing the smell of prey, and to aim themselves towards the source. It is now known that they use a principle called chemotaxis, in which they extract directional information from the composition of the plume itself to do this. How this is achieved, or precisely what information is being used, is not well understood. Somehow the lobster remains in the center of the plume and orients itself towards the source by constantly monitoring changes in the makeup of the plume as it moves. Some researchers believe the downstroke of the annule, which is very fast, captures a high-resolution picture of the plume's structure, while the slower upstroke measures and analyses that structure. On the face of it, these all seem to be examples of goal-directed behavior. But let's consider how they compare. Exercise 4. Given all these cases involve trying to achieve a goal, what differences do you think there are between them? Try to think about the goals themselves as well as the behavior that leads towards them. What part do you think reasoning might play in these activities? Comment. I think that there is a clear hierarchy of complexity here, moving from very simple to extremely intricate behavior. To take the cases in reverse order. In case study 5, the lobster is sensing its environment, doing some internal processing, recognizing a stimulus of interest and then adjusting its responses accordingly, to support its primary purposes of feeding, hiding or mating. The behavior of the gulls in case study 4 is more clearly recognizable as goal-directed and appears more sophisticated. The primary goal is still simple to feed, but in this case, the bird's behavior is underpinned by refined sensory recognition systems estimating the position and geometry of the shell, identifying the right type of rock, judging the texture of the sand, and flexible behavior choosing the right height for the drop, or dropping the shell again, if necessary. Chimpanzees are our nearest relatives genetically, so in case study 3 we find behavior that we could have no qualms about labeling as intelligent. The apes may have a simple goal, a banana, but in other cases it can be more complex and abstract, such as wanting to have a more interesting view, freedom from the cage, and so on. Even more impressively, the chimp can work out how to reach its goal through a series of stages, or sub-goals. Although these 3 cases are, of course, very different, it's difficult to see where one could draw a clear line between goal-directed behavior that is intelligent and that which isn't. The chimp's mentality seems to resemble our own. They have abstract goals, they form plans, they appear to have an excellent grasp of causality. For example, they know, after a bit of thought and experiment, that certain actions will lead to given results. If I use the rod in this way, then the bars will bend. However, be aware of a temptation towards anthropomorphism here. It's tempting to label gorillas as less intelligent than chimpanzees, as they show little interest in, or desire to use, tools. But gorillas are herbivores, living in the wild on a simple and abundant diet of nettles and leaves. They would have little use for tools and, presumably, have not evolved to recognize or use them. But what about the gulls and the lobsters? It would seem quite reasonable to call the lobster's plume tracking goal-directed, even though it is still a fairly straightforward form of stimulus and response that biologists call taxis. Of course, it's hard to imagine that lobsters, which are related to spiders, have any awareness of pursuing an aim, but their behavior is quite intricately purposeful nevertheless. The gulls and crows are even more problematic. At one time, it was common to dismiss this type of behavior as instinctive, as if that explained it away, but repeated experiments have shown that it is learned. What we can clearly see in these cases is the pursuit of basic goals, feeding, etc. through complex, flexible behavior. It's important to reiterate the main point here. None of these creatures possesses a developed language, as humans do, and none of them, with the possible exception of the chimps, could be said to be reasoning about their goals. Chimpanzees can be taught restricted versions of human language, so goal-directed behavior can occur, and be effective, even in the absence of logic and symbols, and it surely seems reasonable to see goal-directed behavior as lying along a spectrum of complexity and sophistication, from the purely mechanical reactions we see in plants through to the complexity of human goals and plans. 2. Systematic behavior. One of the most striking features of army ant attacks, described in case study 2, is just how organized they are. Raids begin at the same time of day. The swarm front develops in an apparently disciplined fashion. Individual ants specialize in specific tasks. Prey items are butchered and returned methodically to the bivouac. The whole collective seems to act with the obedience and control of an army. We noted similarly orderly behavior in the migration of birds. In all cases the animals seem to be behaving systematically, with a regularity that is quite unlike the piling up of rocks by a glacier or the flow of a river. Here is another example of such systematic activity in nature. Case study 6, Nest building paper wasps. The paper wasp Olivia occidentalis is a social insect that lives in large colonies and builds elaborate nests. See figure 6. When a swarm made up of one or more queens and many thousands of workers arrives at a nesting site, nest construction starts with a set of hexagonal brood cells attached to a suitable support, such as a twig. The workers gradually extend this comb of cells outwards to form a disc shape, projecting either side of the support. The queen begins laying eggs in these cells more or less as soon as the construction of the comb starts, and a number of workers immediately take on the task of removing corpses and feces from them. Figure 6 envelope construction is nearly complete. You can see some of the comb cells inside. B workers begin a new comb on the underside of the previous envelope. When the comb has reached a certain size, the behavior of the building workers changes abruptly. They move back to near the point of attachment of the comb and start constructing a dome-shaped protective envelope around it. See Figure 6a. The envelope is extended to completely enclose the comb, apart from an access hole about 1 centimeter wide. As the envelope is finally closed off, building behavior changes again and the workers start to assemble a new comb of brood cells, attached to the underside of the envelope they had just completed. See Figure 6b. Once again, when this new comb reaches a certain size, a new enclosing envelope is started. The workers continue to alternate between building combs and envelopes until the nest is big enough for the whole swarm and their brood. The nest may be extended later, and is kept in good repair for as long as the colony occupies it. Both combs and envelopes are constructed from pulped wood that is moistened and then allowed to dry. Two groups of specialist workers forage for the necessary materials, one for wood pulp and one for water, while a third group does the building. It appears that no wasp is irrevocably committed to one task only. A worker in one group may switch to one of the others, but this does not happen frequently. The activities of the three groups are very closely coordinated. Water foragers supply water to both builders and pulp foragers, who use it to moisten wood pulp, while wood pulp foragers supply material only to builders. The size of the three groups changes constantly according to the building needs of the moment. And, in some way, these relative sizes change to minimize queuing delays. 2. 3 structured and functional results. While the paper wasps provide another example of goal-directed, systematic behavior, perhaps this case study's most noteworthy feature is that not only is the activity of the wasps decidedly regular and methodical, but the end result is also highly structured. There are countless other examples we could cite of animals building serviceable, complex structures, shelters, nests and colonies, specialized tools, and devices to catch prey. Such constructions are all highly functional. They appear beautifully fashioned to serve the particular purpose they were built for. The end product perfectly serves the original goal. Structure and function are qualities we associate with human artifacts. Nature tends to deal in chaotic, fractal patterns. Most of you will have flown high over the land in a jet airliner and observed the scene below. Rivers, mountains and lakes are jagged and irregular in shape. The regular outlines of fields, roads and canals tell us that human activity has shaped the landscape. And all around us are countless examples of human purpose. Buildings, dams, machines, the software we are using to write this course. These constructions are triumphs of humanity's ingenuity and planning. An example I can't resist giving is the breathtaking Neuilly Suspension Bridge in southern France, opened in 2005. With 7 piers spanning a total of 2.5 kilometers across the gorge of the River Tarn, it towers 336 meters above the valley floor, making it the highest bridge in the world, higher than the Eiffel Tower. It took more than 3 years to build and cost $394 million. Figure 7. The Neuilly Suspension Bridge. Complex entities such as these come about through the process that we call engineering. Now, although you probably feel fairly certain you know what engineering is, it's worth giving a moment's thought to the concept. Exercise 5. Imagine you were the manager of the project to build the Neuilly Bridge. Write brief notes on how you might start tackling this problem. I'm assuming you are not an engineer, so I wouldn't expect a very detailed answer here. Try to give an outline of the approach you would take. Comment. Clearly a system this size couldn't possibly be built by one person alone, so you would need to appoint a team. This in turn implies that the work will have to be divided up into parts: design, materials, logistics and planning, testing and quality assurance, for example. Possibly one team member could be placed in charge of each part, and each of them would certainly also want to divide their particular task into work units. You would then have to allocate time and resources to each task and fix deadlines for them. You would probably want to draw up a project timeline and use techniques like critical path analysis to predict areas of possible future difficulty. All subtasks of the main units would also have to be costed and allocated time and deadlines. You would need to set up a strong system of reporting and monitoring to follow the day-to-day running of the project. This is what we might call an engineering approach. Engineering is, of course, concerned with building complex things, usually physical things such as dams and bridges, although software engineers, by contrast, build an intangible entity software. What I think distinguishes it from other activities that involve making things cookery, flower arranging, and so on is that it has to be a highly disciplined and systematic activity. Engineers must plan meticulously, produce careful designs, choose the most suitable materials, conform with all the relevant standards and practices, and work within firm margins of time and money. They will use scientific, technical and mathematical techniques to support this work. One could hardly imagine a more clear-cut example of human intelligence at work. The whole process is obviously ordered and systematic, as one would expect. However, perhaps the most noticeable feature of this strategy is its top-down organization. A single directing intelligence sits at the top of a hierarchy of tasks and control. Work is divided into units, which are in turn divided into subunits and become the responsibility of other guiding minds. Information flows up the hierarchy and control, in the shape of decisions and instructions, passes down. This pattern will be immediately recognizable to you. Many software systems, particularly those built in the earlier days of computing, are structured in exactly this top-down pattern. The design of the systems we build often mirrors the structure of the processes we use to build them. Exercise 6. There are obvious differences between the activity of an engineer and that of nest-building wasps. Quickly note down what you think these differences are. Do you think there are any similarities? Comment. The only similarities I could see between the two cases are that both activities are purposeful, systematic and lead to structured, functional results. As I suggested above, engineering is a disciplined activity that involves planning and design, and is underpinned by the symbolic language of mathematics. Even where mathematical calculation is not involved, the engineer will rely on design drawings and written documentation, both also forms of symbolic representation. It seems incredibly unlikely that the wasps plan their work. Obviously they have no designs to work from, in any sense that we could understand the term. And mathematics must surely be far beyond the reach of an insect. So there can be no doubt at all that wasps are not engineers, yet they behave systematically to produce a regular structure, perfectly fitted to the task it is built for. Of course, it would be idle to pretend that the wasps are making anything as complex as the Mealy Bridge. However, there are similarities between the two cases. Both the human and the insect activity give rise to a structured and functional end product. And both cases involve a number of independent workers whose activities have to be closely coordinated. Nevertheless, despite the similarities, there is a sharp contrast between the two cases. Engineering is a top-down, human approach to a complex problem. The wasps seem to be following a radically different path. There is no overall control, no managing brain, no design, no obvious breakdown of tasks. We refer to this sort of organization as bottom-up. The coordination of the wasp's work can't possibly come about in the same way as that of the human engineers. The necessary mechanisms simply aren't available. For a start, there is no overall controller. The medieval notion that the queen's role is somehow like that of a human sovereign is a fantasy. Queens simply lay eggs. And even if there was some important wasp in charge, there are no obvious ways it could communicate orders to the rest of the swarm. Insects do communicate, as we shall see later, but nevertheless there is no practical means by which messages could reach the widely distributed builders and foragers. However, the insects do seem to work together remarkably effectively, with convincingly practical results. Figure 8. William Paley. Our tendency to take regular, functional structures to be evidence of superior intelligence at work was perfectly expressed by William Paley 1734-1805 in the following very well-known observation from his Natural Theology of 1800. He asks us to imagine walking on a heath and striking one's foot against an object we think at first is a stone, but which on closer examination turns out to be a watch. He goes on. When we come to inspect the watch, we perceive that its several parts are framed and put together for a purpose, e.g., that they are so formed and adjusted as to produce motion, and that motion so regulated as to point out the hour of the day. That if the different parts had been differently shaped from what they are, or placed after any other manner or in any other order than that in which they are placed, either no motion at all would have been carried on in the machine, or none which would have answered the use that is now served by it. The inference we think is inevitable, that the watch must have had a maker, that there must have existed, at some time and at some place or other, an artificer or artificers who formed it for the purpose which we find it actually to answer, who comprehended its construction and designed its use. Source: Paley 1800, Chapter 1. Let's now try to round off this discussion of natural intelligence, first with a brief recap and then with some conclusions. Sac 2. Write brief definitions of goal-directed behavior, systematic behavior and structured and functional results, as they've appeared in this section, giving one example of each. Answer. Goal-directedness is simply acting in such a way as to reach some clearly defined objective, such as when a homing pigeon flies back to a fixed place, or an animal forages for food. I've given a number of examples of behavior that are systematic, that is, they seem to follow a pattern or some fairly rigid process. Organized hunting behavior, systematic construction of nests and shelters, etc. Lastly, I noted that such systematic activity can result in highly regular and functional products, structures perfectly suited for a particular purpose too. For some conclusions. Some naturalists and ethologists insist that animals are completely without thought, mentality or conscious awareness. A few others, such as Donald Griffin, believe that even quite simple creatures may have mental states comparable in kind to our own. See Griffin 2001, from which many of my examples have been taken. The majority do not want to commit themselves, but generally avoid questions about animals' mental life with distaste, on the grounds that mental states cannot be observed directly, so talk of them is unscientific. Boakes writes, attributing conscious thought to animals should be strenuously avoided in any serious attempt to understand their behavior, since it is untestable, empty, obstructionist and based on a false dichotomy. Source: Boakes 1992 Subjective Experience, Times Higher Education Supplement. Fortunately, we do not need to take sides in this debate, which I think has been bedeviled by misunderstanding, prejudice and muddled thinking. Animals may, or may not, be consciously aware of what they are doing. The main point I've been trying to make in my choice of case studies is simpler. It is that behavior we would be inclined to label intelligent can be seen on a continuum. Einstein was intelligent. We would almost certainly want to say that the chimpanzee using a tool to get at a banana is acting intelligently. Clearly a plant isn't intelligent. How could it have a mind in any conceivable sense? But what about migrating birds, nest-building wasps or foraging gulls? It seems irrational to draw a firm line somewhere in nature and say here intelligence begins. And it is surely anthropomorphic to draw that line under Homo sapiens and exclude all else. Every organism in the natural world has problems to solve, what David Attenborough once called the trials of life. How to find food. How to avoid becoming food. How to find a mate. How to navigate safely around a hostile and dangerous world. All existing animals have devised workable, if imperfect, solutions to these problems. And so computer scientist Luke Steels has defined intelligence as success and self-preservation. Now it seems most unlikely that wasps reason about how to build their nests or consult blueprints. Birds do not have printed maps to guide them. Nor do ants have charts of their territory or control their armies with orders. No animals other than humans appear to have language in any truly developed sense. Still less I believe does nature itself have a rational plan for its own development. But nature has found ingenious answers to the trials of life. It has its own forms of intelligence. All of our case studies were chosen to suggest that this natural intelligence, if we understand the term in a suitably liberal sense, may be widespread in nature, and that anthropomorphic definitions of the idea might not tell the whole story. My aim now is to move away from, and to contrast, the general idea of intelligence as being exclusively human intelligence. Sac 3. Try to recall some of the characteristics of human intelligence that Al seeks to represent and replicate on machines. Answer. We came up with the following list. Knowledge. Rational thought using symbols to reason with, as in logic and mathematics. Language using symbols to communicate in speech and writing. The ability to make plans, design and foresee. The ability to learn specialist knowledge and skills. You might have been able to come up with some other plausible ideas. Now, let's try to use this to draw some conclusions about natural intelligence from what we have learned so far. If we can agree that, in general terms, intelligence can be recognized in activities that appear goal-directed, systematic and ordered, what might this suggest about animal intelligence? Exercise 7. Look back at case studies 1 to 6. What mental or behavioral capacities do you think the various animals discussed there would need to produce the goal-directed, systematic behavior we observed? Based on your general knowledge, can you think of any additional abilities that might be necessary, and that some animals may possess? Try to think clearly about the case studies and develop a broad conception of intelligence, one that doesn't presuppose logic, language or formal, explicit thought. Comment. This is probably the most challenging exercise I've asked of you so far. However, I think it is definitely worth carrying out. I arrived at 6 mental and behavioral characteristics that I thought were demonstrated, at some level or other, by most of the animals in the 9 case studies. Drives, recognition, classification, response, communication, learning. You may have come out with different ideas, but let's look at each of these 6 in a little more detail and extend our analysis beyond the human sphere. Drives. At the root of every form of animal behavior there seem to be basic drives. Living creatures have purposes in what they do. We are all familiar with the complexity of human motives. Why am I writing this course? Naturally, I want to earn money to eke out my paltry existence. But I also have other, less tangible reasons: creativity, professional pride, desire to convey ideas I think are interesting, and so on. Why are you studying M366? Presumably, your purposes are many and various. Animal drives tend to be simpler, of course. At the root of everything lies the battle for survival, which can be boiled down to what the philosopher Dan Dennett once memorably called the 4 F's. Feeding, fleeing, fighting and finding a mate. Without drives, intelligent behavior or behavior of any sort other than randomness simply wouldn't happen. Recognition. In the case studies, we noted that birds navigate with reference to stars and landmarks, lobsters detect prey in waterborne plumes, etc. Even the humblest creatures sense their environment. Single-celled amoeba are sensitive to light, for instance, but with increasing sophistication comes an increasing ability to recognize and discriminate. A lobster can tell the difference between a plume given off by a predator and one indicating a possible mate. Herring gulls can tell the right type of dropping zone from the air. Chimps recognize each other as individuals. In all these cases, what the animal is identifying is a complex pattern of features, a special configuration of stars, or a suitable combination of flatness, hardness and physical position relative to the waterline on a rock. This ability to recognize patterns as a whole will be a topic of major importance in the course. Classification. Along with this ability to recognize comes the related ability to classify or categorize the things that are sensed. We've seen in the case studies that migrating birds can distinguish some landmarks and constellations from others. Lobsters can classify plumes into friend or foe. In a very well-known experiment, a plane towed the basic shape illustrated in Figure 9 across the sky above fields in which birds were feeding. If the object was towed in orientation A, the feeding birds below took no notice the moving shape resembled a harmless goose. However, when towed in orientation B, the shape immediately came to resemble a predatory hawk, and the birds below all went into avoidance and hiding behavior. Clearly they were able to classify shapes at least into the simple categories dangerous and harmless. Figure 9 Bird Recognition and Classification Experiment. Humans deal with the complexities of the world by means of an intricate system of concepts in which whole families of phenomena are classified under one label. For example, the tag tree covers the entire vast collection of things we call trees. This ability to categorize seems to be related to our capacity for language. We use a semantic marker, a word, to stand for a whole mass of features and individuals. Whether animals can have a conceptual system of any sort is a matter of fierce debate among ethologists and behavioral psychologists. No animals have a language of any sophistication, so if they have any system of concepts at all, it is bound to be limited. Various experimenters have reported work in which chimps can be taught to count numerical sequences. Pigeons can learn to discriminate between categories such as picture with a person in it and picture without a person in it, and even between some geometric shapes presented in various sizes and orientations. But there is little agreement over how such results should be interpreted, and the whole question is clouded by anthropomorphism, as the case of Clever Hans, which I discuss below in case study 7, indicates. Response. By this I mean rather more than the fact that animals react appropriately to the stimuli they receive. A simple creature like a lobster or an ant seems to have a fairly limited range of responses it can make. The lobster, for example, when it detects a plume, can choose to move towards it or away from it. However, although such reactions may appear straightforward at first sight, they conceal deep complexity. As I stated, it is by no means understood how the lobster maintains itself in the center of the plume and selects the right direction to move in. And consider the elementary action of catching a ball. We wouldn't be inclined to call it intelligent. Anyone can do it. Dogs can be trained to do it. But, although we aren't aware of it, we are performing complex calculations in real time as we move to make that clean catch. Even actions to which we would not give a single thought, such as walking and handling objects, turn out to be massively complicated processes. But the most important point here is that animals are active. They move around the world. They are intimately involved with it. They are constantly required to respond to its demands. And they shape it to suit their needs. It is in this activity that the roots of intelligence lie. In a science fiction novel of 1930, Last and First Men, Olaf Stapledon pictured a future time in which humanity decides to construct several huge brains, without bodies, suspended in vats, intended to solve all the problems of knowledge through pure intellect. Man, they said, is a very noble organism. We have dealt with other organisms so as to enhance in each its noblest attributes. It is time to do the same with man. What is most distinctive in man is intelligent manipulation, brain and hand. Now hand is really outclassed by modern mechanisms, but brain will never be outclassed. Therefore we must breed strictly for brain. We must produce an organism that will be no mere bundle of relics left over from its primitive ancestors precariously ruled by a glimmer of intelligence. We must produce a man who is nothing but man. The governing caste were strongly opposed to this policy. Man, they said, was essentially an animal, though uniquely gifted. His whole nature must be developed, not just one faculty at the expense of others. Source: Stapledon 1930 Last and First Men, p. 208. So it proves. The great disembodied brains are built, but the great brains had a growing sense that though in a manner they knew almost everything, they really knew nothing. The normal mind, when it experiences intellectual frustration, can seek recreation in companionship, or physical exercise, or art. But for the brains there was no such escape. These activities were impossible or meaningless to them. Ibid. p. 215. But actually it would be much worse than this. A brain without a body could never have evolved intelligence. It would not think at all, for it would have nothing to think about. Communication. I didn't stress this in my discussions of the case studies, but it is certainly implied in them. Some of those animals work together collectively, the ants and, to some extent, the birds. We will look more deeply at such communal behavior early in the next unit, but it seems fairly obvious that cooperative action couldn't be achieved without some form of communication between individuals. Many animals do have elementary languages, systems of signaling to one another. But without syntax, subtle semantics, or verbal association, these have nothing remotely resembling the power of our languages. Learning. Again, this did not appear explicitly in the case studies. However, remember that migrating birds have been shown to learn the shapes of the constellations and landmarks by which they navigate. And oyster catchers discover their feeding preferences from their parents. Learning seems crucial for intelligence. An animal that is inflexible, that has no capacity to change in response to experience, will be a poor contender in the struggle for existence. We'll return to this point in the next unit. Learning will be a major issue in the remainder of the course. Now let's use an SAQ to consolidate these ideas. SAQ 4. Look back at the 6 case studies and for each of them note down which, among the above 6 characteristics, seem to be necessary for the behavior portrayed. Answer. My answer is as follows. Case study 1. Drives, recognition, response and communication, probably classification and learning. Case study 2. Drives, recognition, response and communication, classification and learning are possible but unlikely. Case study 3. Drives, recognition, classification, response and learning. Communication is not implied by the particular case study, but we know that chimps, which are gregarious animals, have sophisticated forms of communication and can even be taught the rudiments of human language. Case study 4. Drives, recognition, classification, response and learning. Case study 5. Drives, recognition, classification and response. Case study 6. Drives, recognition, classification, response and communication. You may have come up with rather different ideas. The whole area is difficult because we are having to infer mental properties, if animals have mental properties at all, from outward behavior. 2. 6. A dreadful warning. Finally, a case study to serve as a warning against the ever-present danger of anthropomorphism. Case study 7. Clever Hans. Hans von Ausen lived in Berlin around the turn of the 19th century and was famous throughout Germany for his ability to solve mathematical problems such as 3x4 or 3x9. Not so special, you might think, but Clever Hans was a horse. His owner, Herr von Ausen, would write an expression such as 2x3 or 5x2 on a blackboard, and Hans would respond by tapping the ground with his hoof the right number of times. He sometimes got the answer wrong, but his success rate was much higher than chance. People came from far and wide to watch Hans's act, and many scientists of the time accepted that he understood arithmetic and could calculate. Exercise 8. What do you think? Are other explanations possible? Did Hans understand arithmetic? Could he calculate? Comment. Alas, no. The psychologist Oscar Funkst was able to show that Hans was not even looking at the blackboard, which we may assume meant nothing to him. He was watching his master. He had learned to pick up tiny, unnoticed scraps of body language which told him when was the moment to stop tapping his hoof. If no one was present as the problem was presented, he simply tapped at random. Earlier in this unit we defined anthropomorphism as a tendency to call behavior intelligent only if we can identify it with our own. Anthropomorphism is an ever-present danger when we try to make inferences about animal intelligence. Here we have an inverted case of the same problem. Looking at Hans's behavior, it is all too easy to imagine he had mental states and awareness of number and sequence, an appreciation of the meaning of arithmetic operators which he simply did not possess. He was a horse. The mental world of horses, if they have one at all, must surely be utterly remote from ours. 2. 7. Natural, artificial, living. 2. 7. 1. Natural and artificial things. So far, we have been looking at intelligence in the natural world. At this point in the discussion, it is worth pausing briefly to consider whether intelligence is exclusive to nature and natural systems. If it isn't, where else might intelligence be found? This seems a reasonable question, given that our goal is to build intelligent computer-based systems, artificial systems with intelligent capacities. But what exactly is an artificial system? What does it mean for something to be artificial, as opposed to natural? Nature can be defined in countless different ways. The character of each definition is largely determined by who is proposing it, for example, a philosopher or a biologist, and the purposes for which it is intended. This section will give you an idea of the wide-ranging and often conflicting ways in which philosophers and scientists have interpreted the idea of nature. Exercise 9. Spend the next few minutes trying to come up with your own definition of the term nature. Comment. You might have come up with one or more of the definitions in the following list, which is not intended to be exhaustive. The essence of a thing, its core or inner reality. As in, for instance, the statement by his very nature, he is cautious. The sum of all natural things. You can probably see at once that this definition is circular. Nature is defined in terms of the natural, which remains undefined. All the things in the world that have originated without human influence. All living things, either including or excluding humans. The structures, processes and laws that make up the world, which are studied in the natural sciences and which scientists, technologists and engineers seek to harness or to modify. For our purposes, we might perhaps settle on the smaller set of definitions proposed by Frederick Fair in The Philosophy of Technology 1988. Nature is all that exists in the evolving world of space and time. Nature as that which is essential in a thing, that is, that which is expressed, all other things being equal, when it develops according to its kind without outside interference. Nature as the collective term for all that exists apart from the artificial. Sac 5. Read over Fair's 3 definitions again. Do you detect any problem with them when they are taken together? Answer. You may have spotted that the set of definitions is inconsistent. Definition 1 states that nature is everything that exists, which would have to include all artificial things, yet the artificial is explicitly excluded from nature in definition 3. Clearly, either everything is part of nature, in which case the artificial cannot be something other than nature, or everything is not part of nature, in which case there is a distinction between nature and the artificial. If we want to make this distinction, then we have an obvious duty to define what we mean by artificial. In his book The Sciences of the Artificial 1981, the pioneering computer scientist Herb Simon identifies the following list of features as characteristic of artificial systems. They are constructed, though not always, or even usually, with full forethought by man. They may imitate the appearances of natural things but lack, in one or many respects, their reality. They can be characterized in terms of functions, goals and adaptation. They are often discussed, particularly when being designed, in terms of imperatives, that is, in terms of how a thing ought to be, as well as descriptives, that is, in terms of how a thing actually is. Simon maintains that the artificial arises from applying human rationality to the design of objects. If this rational design process is somehow analogous to evolution, then artificial things in some ways resemble natural things. There are clear echoes here of Paley's argument, which you met earlier in section 2. 2. Most higher organisms give the impression of having been superbly designed for their various purposes. However, the majority of scientists don't accept the theory of intelligent design. They see structure, order and pattern as arising from blind, impersonal forces through evolution or other processes. So although we are usually inclined to see the products of human activity as artificial and animals and plants as natural, for Simon the distinction breaks down. In his view, artifacts are designed by humans. Organisms are designed by nature. The boundary between artificial and natural becomes even more blurred when we turn from the rational, top-down design of artificial things, such as bridges or computer programs, to the bottom-up design of artificial things by means of techniques that are inspired by natural processes, such as Darwinian evolution by natural selection. 2. 7. 2 living things. Throughout this unit, we've been discussing animals and plants as living things, members of a distinct, biological kingdom, as if it was self-evident what life actually is, and that the distinction between living things such as parrots, spiders and humans and artifacts such as bridges, spoons and computers is clear-cut. At first glance, the distinction does seem self-evident. Surely we all believe that there is a sharp division between systems that are biological, or living, on the one hand, and non-biological, or inanimate, on the other. We would generally have no trouble in assigning an anteater to the first and a computer to the second, but, as so often, such a clear and obvious separation may not stand rather closer scrutiny. Think about this difficult question. Exercise 10. What makes something biological? What makes it living as distinguished from something that is non-biological and non-living? This is a huge question, so don't dwell on it for too long. Just jot down one or two possible answers. Comment. Arriving at a hard and fast definition of life as a basis for distinguishing living from non-living things has proved very difficult, if not impossible. The Oxford English Dictionary defines biology as the science of physical life, but this hardly helps. It's another piece of circularity. Some scientists would want to say that biological systems depend on complex interactions between certain types of organic molecules, notably DNA, amino acids and proteins. They might offer a rough definition of a living thing as one that shows evidence of all of the following at least once during its existence. Growth metabolism. It maintains itself by taking in, storing and using energy and expelling waste. Motion response to stimuli. Reproduction. Unfortunately, as you can probably see, these definitions can easily be broken down by counterexamples. A cast iron definition of life, and even of biology, has eluded science. Certainly, all known biology depends on certain complex organic molecules, but so do many other systems that we would not consider to be alive. Crystals grow. A laptop computer takes in energy, stores it, uses it for computations and radiates waste in the form of heat. Cars move under their own steam. And thermostats respond to changes in their environment. Viruses, which are only questionably alive, reproduce themselves, according to the Oxford Companion to Philosophy. Efforts to find some distinctive substance characterizing life have proven as futile as they have been heroic. The one thing which is clear is that any analysis of life must accept and appreciate that there will be many borderline instances, like viruses. Source: The Oxford Companion to Philosophy 1995. Many scientists believe that the definition of life question is a red herring. Life, they say, exists on a continuum. There are no simple alive, not alive decisions to be made. A rock would certainly be low on any continuum of aliveness. A dog, a tree and a human would rank highly. Some systems would fall in the middle region of semi-aliveness below bacteria, which almost everyone agrees are alive, and some way above rocks. Viruses would fall somewhere in the upper reaches of this middle ground. Below them would be complex systems that no one really considers to be alive but that display some behaviors consistent with living organisms, things such as the economy and cars. The observation that all living things are built on an organic substrate is not particularly useful either. There are no grounds for asserting that biology must depend on organic molecules. Some scientists call this belief carbon chauvinism. Indeed, one could make a persuasive case for the idea that the more sophisticated kinds of computer viruses also fit most definitions of life. They certainly move, respond, reproduce and share the metabolic properties of the computer, although there is nothing organic about them. But ordinary common sense would seem to insist that they cannot be alive. These discussions are not irrelevant to the concept of artificial intelligence. If we accept that the distinction between natural and artificial, biological and non-biological is not clear-cut, that natural things don't necessarily have to be built on an organic substrate, and that intelligence, in the sense of successful, goal-directed, problem-solving behavior, is widespread in the natural world, then a study of how intelligence of this broader kind comes about could have profound implications for the kinds of systems that computer scientists write. We can now move on to explore some of these implications. 3. Natural and artificial intelligence. In this unit so far, you've read 3 sections and 7 case studies, puzzled over 10 exercises and answered 5 SAQs, and all with scarcely a mention of computers. Plenty on natural intelligence, almost nothing about artificial intelligence. Now is the time to set that right. Our aim is to build intelligent machines. In this final section I want to extend the discussion of computer intelligence in the light of what you've learned so far about natural intelligence. This will lead us to consider the possibility of novel techniques, yield fresh insights into old problems, and suggest how new problems might be brought within the scope of artificial intelligence. My analysis should set the stage for the rest of the course. 3. 1. Intelligence and knowledge. Most computer systems are written in response to some kind of requirement, for instance the need to process text efficiently or to move robots around, or as a means to answer complex questions. Just to take a few examples at random, the following questions are all ones which we might design computer systems to answer. What are the names of all the employees who are left-handed and speak Mandarin Chinese? What would be the effect on profits of increasing production by 5? What will the weather be like tomorrow? Computers solve any problem by stepping through a suitable algorithm. For many requirements, such as sorting, searching or mathematical operations, there are well-known algorithms that work efficiently in real time. Some problems succumb to brute force algorithms. However, many serious problems seem to require processes into which some measure of intelligence has been blended, if they are to be solved within realistic timescales or at all. SAQ 6. Give 2 specific examples of problems that conventional artificial intelligence programs have been written to solve. Answer. All sorts of answers are possible. Computer translation, expert diagnosis, planning, robotic movement, etc. all come to mind here. I've argued that the AL approach to automating processes requiring intelligence originates from an anthropocentric picture of intelligence, one based on knowledge and reasoning. The AL story is that we are able to understand the workings of our cognition by looking into our own minds, representing what we find there in some formal way, and then translating this representation into a symbolic form that can be handled by a computer. However, a moment's introspection should convince us that there are limits to introspection itself. Consider this case. One technique still widely used in AL is to represent human knowledge as a series of production rules of the form if, then. Human experts, doctors, chemists, geologists are quizzed in lengthy sessions of knowledge elicitation to draw out their knowledge and represent it in the rule-like formalism shown above. This can then be transferred to a computer where it can be processed by algorithms. However, now consider another human activity, one in which most of us are expert. Riding a bicycle. What are the rules for doing that? Clearly, we could sit together all day and you wouldn't be able to tell me. It just doesn't seem to be the sort of thing that can be expressed as rules or expressed at all, really. We just do it. It doesn't appear to involve any explicit thought at all. Exercise 11. Try to think of 2 similar activities you carry out without apparent thought. Comment. Examples are walking, catching a ball, swimming, etc. In fact, everyday human living comprises countless activities that we seem to carry out without any reasoning at all. Of course, we had to learn to do them at some time. But this learning process didn't really resemble formal teaching, of the kind you're undergoing now. I certainly didn't learn to walk by being taught the rules of ambulation. AL stresses the importance of knowledge, but knowledge is not necessarily a single kind of thing. Philosophers have long distinguished between 2 kinds of knowledge: prepositional and non-propositional. These 2 can be understood as follows. Propositional knowledge is knowledge that can be expressed explicitly in the form of propositions, such as the Battle of Hastings was in 1066, or the light from distant galaxies shows a redshift. It is sometimes called knowing that, since you can precede each proposition with the phrase "I know that the sun rises in the east." Non-propositional knowledge is knowledge that can be expressed in this way, usually because it is manifested in some form of ability or skill. Examples include I know how to swim, I know how to speak French, etc. So non-propositional knowledge is often called knowing how. Non-propositional knowledge is also sometimes called tacit or implicit. Other classifications have been attempted, but I won't consider them here. Sac 7. Give 2 examples of prepositional knowledge you possess, and 2 of non-propositional. Answer. I know that Java is an object-oriented programming language and that Shakespeare wrote King Lear. I know how to swim and how to speak English. The last example in the SAQ's answer is worth a moment's discussion, since language is so close to the heart of our intelligence. More or less every normally reared human acquires language. Human languages are fiendishly complicated, rule-governed structures without rules of some kind. A language could hardly be a language. However, if I were to ask an average speaker to state the rules of their language, it's very unlikely they would be able to do so. Only professional grammarians really have any explicit knowledge of linguistic rules, and even then they seldom agree. So speaking a language seems to be a matter of following rules without even knowing propositionally what those rules are. It is a classic example of non-propositional knowledge at the core of our mental life. 3. Tu nouvelle au. We needn't argue over what proportion of human knowledge is non-propositional. It's enough to say that an immense mass of human knowledge and faculties, much of it central to our lives, seems to be tacit in this way. It cannot be reached by introspection. Most of the workings of the human mind are hidden from us. The majority of psychologists would agree that what you see when you look into your own mind is only a small fraction of it. The explicit, rational, symbolic part of our minds is only the thin, visible surface layer of an ocean of cognition. The argument in this unit has been this. Look at nature and everywhere you will find cases of non-propositional forms of intelligence. Animals solve problems constantly, without any need for symbolic reasoning. We do too, although we are symbolic reasoners as well. An understanding of this natural intelligence might help us with some of the problems that conventional AI has failed to solve. If we can work out how goal-directed, systematic, ordered problem-solving behavior arises in the absence of rationality and planning. If we can make sense of the mechanisms that allow both animals and ourselves to perform complex actions without conscious thought, and if we consider how these can be replicated on a computer, then this could have the following effects on our research. New computational tools, techniques and approaches may become available, and these may yield new insights into the classic problems of AI. New fields of inquiry may be opened up. Many problems that seemed irrelevant to earlier researchers, or simply did not look open to representation on a computer, probably because they involved non-propositional knowledge, might become solvable. Some commentators have suggested that conventional AI has concentrated only on problems that are amenable to computer solutions. Games like chess are a good example of this, and then labeled the processes required to solve them as intelligent afterwards. A classic circular argument. The project to bring insights about the mechanisms underlying natural intelligence to difficult computational problems is called biologically inspired computing, or often nouvelle AI. Our aim is to consider what these mechanisms are, how systematic, ordered, purposeful behavior can arise without explicit representation, and to offer detailed examples of how they can be applied in real computer systems. The discussion becomes less and less biological as it proceeds, although I will still refer to concepts taken from biology and to examples taken from the natural world. 3. A final caution. It may seem that I've been trying to refute or belittle symbolic AI to show that it is in some way discredited or simply wrong-headed. This is not so. I do not believe that AI is a failure, or that it is in any way a completed project. It is an ongoing and vital area of research that has had many successes. Like some other areas of technology, it has perhaps become the victim of these successes. Starting with early promise and much hype, most of it not generated by researchers themselves, it has failed to produce sentient androids or superbrains that keep humans as pets, but has moved modestly into the mainstream. Computer systems based on ALP principles now reside quietly in washing machines, websites and wireless networks. And ALP discoveries have influenced numerous other areas of computing. Predictably, the response has been pretty much that prophesied by the software scientist Bertrand Meyer. The well-known three-step sequence of reactions that meets the introduction of a new methodological principle. 1. It's trivial. 2. Besides, it won't work. 3. Anyway, that's how I did it all along. The order may vary. Source: Meyer 1997 Object-Oriented Software Construction, p. 1. Every searcher after a new idea should have a copy of this observation pinned to the head of their bed. Summary: in this unit I've sought to extend and contrast the conception of intelligence by looking at the behavior of a range of animals. We arrived at an understanding of natural intelligence as, broadly, goal-directed, systematic, ordered problem-solving, and considered the meaning of each of these terms. After challenging the conventionally accepted distinctions between natural and artificial entities and between biological and non-biological systems, I then moved on to reflect on the possible influence of a broader understanding of the concept of intelligence on the project of artificial intelligence. Now look back at the learning outcomes for this unit and check these against what you think you can now do. Return to any section of the unit if you need to. Next steps. After completing this unit you may wish to study another OpenLearn study unit or find out more about this topic. Here are a few suggestions. Machines, Minds and Computers M366 1. Science, Maths and Technology. If you wish to study formally at the Open University, you may wish to explore the courses we offer in this curriculum area. Natural and Artificial Intelligence M366, Computing and IT. Or find out about studying and developing your skills with the Open University. Study Explained. Skills for study. Or you might like to post a message to the unit forum to share your thoughts about the unit or talk to other open learners. Review or add to your learning journal. Rate this unit.